Hi folks, this is the first of several tutorials on the gases. And as you pursue this area of study, one of the first things that's going to be important is to have in mind a sort of model or picture of how we imagine gas particles are moving. The little diagram here in this first slide illustrates kind of how we think about gases. Your body is surrounded by literally billions of air molecules which are continually colliding with our body. Each individual atom creates a force where it hits your skin, but the combined effect is a force which acts on the total surface area of your body. And this creates the phenomena of pressure. It also relates to the temperature that we feel as well, because as these atoms slam into the molecules that make up our skin, they transfer energy, kinetic energy, to our body, and we feel that in the form of temperature. So again, this video or this tutorial is just meant to show you some of the basic equations that we use to describe what happens to gases when several changes are made to them. So the first sort of equation to look at is the one that we use to define pressure, and pressure is defined as a force divided by an area. And in this little problem sample calculation, we're going to be calculating the force that acts on a certain area. So the first thing you might want to do is to manipulate the equation around so that you're finding the thing that you want to find here, which is the force. So this relates to a demonstration, kind of a magic trick that we did in class, which is the amazing levitating water trick. If you recall, we flipped over a bottle and the water appears to stay in an opened bottle. And this is the trick is achieved by putting a small plastic disc on the bottom of the bottle, and somehow the water stays in. This is because the force of the air acting on the water is greater than the weight of the water, which is in the bottle. And this is due to, as we discussed in class, something called Pascal's principle, which says that the air pressure that acts on us acts in all directions. So normally the air pressure at sea level is about 14.7 psi, which means that there's about 14.7 pounds acting on every inch squared of your body. And this acts downward, it acts from the side, and it acts in an upward direction as well. So, so the water feels about, well, we'll figure out what exactly in this case, a certain amount of force that in this case, as I said, is greater than the weight of the water. So enough rambling here. Let's take a look. So we have an equation, and we have some information that we can plug into this equation, but as always, it's important to consider your units that you're using here. Since we're asked to find the force in pounds, we need to convert the pressure unit 753 torr into psi, using the conversion factor that 14.7 psi is the same or equivalent to 760 torr. So the area, it's a circular area, so the area of a circle is pi r squared. That gives us the area of 0.636 inches squared. And then simply plugging this into an equation, you can see now that our units cancel appropriately here. And we get that the force acting on this little disc is about 9.26 pounds. And that's greater than the weight of the water that is above that cylinder, or above that circular base, and therefore the water stays in the jar. All right, moving on. So, as I mentioned earlier, there's a number of gas laws here that you can study. Sometimes they're broken individually into different gas laws, and you can study and memorize all these different equations. But it might be easier just to, if you're going to memorize something, memorize the one equation that I have here, which is in blue. And we can show you how that can be broken down into individual equations, which sometimes go by the name of famous scientists that did some work to develop these. The first one that's often discussed in any lesson on the gases is something called Boyle's Law, which is in honor of Robert Boyle, who was a very famous chemist. He is considered by many to be sort of the founder of modern chemistry because of the work that he did, and also a pioneer of the scientific method. So Boyle noticed that that if you have a container like the one shown on the right here, and we have a certain amount of trapped gas in there, if you exert a pressure on that, the volume will go down. So if you increase the pressure on the gas, the volume decreases. If you reduce the pressure, the volume will increase, and this is called an inverse proportion. So, so you can see where this comes from. In this case, we're keeping the number of gas particles constant as well as the temperature, so they can cross out of the master equation, if you want to call it that. And this is where you get Boyle's law. So Boyle's law is looking at the effect of pressure on the volume of a gas, assuming that the number of particles and the temperature is held constant. So let's look at this as an example problem. Suppose we have a gas which originally occupies some 5 liters at a pressure of 98 kPa, and we're going to increase the pressure to 150 kPa. So just doing your algebra, you can divide both sides by 150, solve for V, and we get about 3.27 liters. Now, this works fine, except that it really, in the end, would be better if you could kind of imagine what's going on here and not have to memorize all these different equations. So let's take a look at a way to do this that doesn't involve memorizing equations. And I know sometimes students are resistant to doing this kind of thing because it involves a deeper thought process, but in the long run, you know, you'll really make your life a lot easier if you understand what's going on here, and you'll probably never forget what's happening. And on top of that, you know, you're going to be exercising your mind to think in some abstract ways. So let's see how that would work. All right. So we have basically 3 numbers that we're dealing with here, and we know that we're trying to find the volume. That means mathematically that you can only arrange these numbers in one way so that the pressure units cancel. That means we're going to take a volume times a fraction of pressure over pressure. And you should think about this and convince yourself that that's true before you kind of proceed with this. So we're going to put the numbers into this little equation, and so it's going to be 5 times a pressure over a pressure. Now, the question always is, you know, well, what number, which pressure do I put on the top of that fraction? This is where you have to envision what's going on. So you got to picture some kind of cylinder in your mind, like the one shown on the right, and imagine increasing the pressure on it. If you can picture that, then in your mind you'll see that the volume is going down. So mathematically, we're going to make that happen by putting the smaller number on the top of the fraction and the bigger number on the bottom. You create a number that is less than 1, and when multiplied times 5, will make it go down. So we're sort of making the math do what we want it to in this case. And the advantage is that, again, you don't necessarily have to memorize a bunch of equations. So I'm going to suggest you try that. I understand that not everybody you know, is ready for that kind of thing, but again, the more you practice at it, after a while, it becomes sort of obvious that that's the way it should go. So let's take a look at another example. Again, all of you that are watching this video are smart enough to plug into the equation and get your answer. So I'm not going to show that right now. I'm just going to show you how to solve these problems in the manner that I just described. So another law that is sometimes referred to as Charles' law looks at the relationship between the temperature and the volume of a gas. Jacques Charles was a French scientist who was very interested in lighter than air travel. In fact, he is recorded as being the first person to launch a hydrogen-filled balloon. It took him several days to fill a balloon by a reaction of sulfuric acid and some iron. He launched this balloon at the site of the now present-day Eiffel Tower, and it flew for several miles, and it landed in a village. And the story is that the villagers were so frightened by this object that they attacked it, thinking it was a monster. So let's take a look at Charles' law. Again, if you can kind of picture what's going on here, in this case, we're saying that we're going to leave the pressure alone and also the amount of gas, and we're just going to see the effect of temperature on the volume of a gas. And again, with the picture that's on the right in your head, if you can imagine heating up a gas, as you heat up the gas particles, they're going to increase their kinetic energy. They're going to move faster. And initially, they'll exert a greater pressure on that piston. But since we want we're allowing the pressure to stay the same, this means that the piston will go up. It'll increase the volume. So this is what we call a direct proportion, a direct relationship. So as the temperature increases, the volume increases. All right, so let's take a look at a sample problem. Suppose you have a gas which occupies a volume of about 300 milliliters. It's at 25 degrees, which is about room temperature. And maybe you put it into a beaker of some boiling water, which is at 100 degrees. And the question is, all right, what's the new volume going to be? Well, a common mistake when doing these problems is to just plug into the equation with the numbers that you got there. But if you did that, you're going to end up with a wrong answer. And that's because you can't use the Celsius scale in any of the equations that deal with gases. The main problem with the Celsius scale is that it's got negative numbers. And if you start plugging negative numbers into this equation, you're going to get negative volumes. And just the thought of a negative volume can hurt your brain, so don't think about that too much. So you have to convert the temperature here to Kelvin by adding 273, which I think hopefully everybody knows how to do. Now you can plug into an equation, or I should say, think about how to orient your units in such a way that they're going to equal a volume. So we have three numbers here. We have milliliters, we have and two temperatures, and we need to mathematically make the temperature units disappear. So if you look at what I've written here, this is the only way to arrange these three numbers so that you end up with milliliters. We need to cancel the Kelvin unit. All right. Now, once you have that in your head, now just think about what's going to happen here. The temperature's increasing. The kinetic energy of those gas particles increase, and that's going to make the volume go up. Picture this in your head. Now, that means in order to make that number go up, we need to have the larger number on the top and the smaller number on the bottom. This will give us a ratio, a fraction, which is greater than 1, and when multiplied times the 300, gives us a bigger number, 375.5. You can check to see whether or not you've gotten the right answer by verifying what you thought in your head was correct and the number that you got. Okay, so here's another example of this kind of process. This one I'm calling Gay-Lussac's law, although Gay-Lussac did a tremendous amount of work on the study of gases. He was also really interested in lighter than air travel. He was truly an adventurer. He was the first person to launch a manned balloon flight, which went to a height of, I think, about 23,000 feet, which stood as a record for, I think, many decades. He was also very gracious in his collaboration and his work that he did with Charles, and he credited some equations to him. So he did a great deal in that regard. Some of his work was later evolved into Avogadro's principle, which is something that we'll take a look at later, but really interesting guy. Okay, so let's consider what happens to the pressure of a gas if we are changing the temperature. And we're going to keep the number of gas particles and the volume constant. So in this case, you're going to picture the diagram that we have here on the right. Imagine taking a gas which is cold, and we're going to heat it up, and it's in a container which is closed. Suppose that we have a gas which is originally at 1 atmosphere, and the temperature is at 0 degrees, and we're going to increase the temperature to something around 200 degrees, and we're wondering, okay, what's going to happen to the pressure? So again, you can certainly just plug into the equation, but let's just think about this. We got 3 numbers again. First thing we're going to do is convert the Celsius temperatures into Kelvin temperatures, and then arrange our numbers considering them from a dimensional analysis perspective. The only way to get atmospheres out of this is to cancel the Kelvin temperature. Again, now we're going to picture what's going on here in our minds. The temperature is increasing. Gas particles will move faster, and that should make the pressure go up. So I'm going to put the big number on the top of that fraction and the smaller number on the bottom. And so when you do that, you get a pressure which goes up, and that kind of confirms what we thought would happen as well. All right, almost done here. Finally, let's we could go on like this and look at lots of different iterations of that kind of thing, but let's just now look at a situation where everything is changing all at once. So in this case, we're going to imagine an apparatus where we have a plunger which allows us to change the pressure. We also have some kind of temperature device which allows us to increase or decrease the temperature of the gas. And now we also have a valve attached to this which allows us to add or take out the gas particles. So let's imagine changing all sorts of stuff here. We're going to imagine that we're initially at a pressure of 750 torr, and we're going to change the pressure to 500 torr. The temperature initially is 300 K, and the final temperature is 250 K. We're going to add some gas, so the number of particles is going to increase and is typically measured in moles. We're going from 3 to 4 moles. The original volume is 6 liters, and we're going to try to find out what the new volume would be. So first of all, whenever you're doing these problems, you want to focus on the numbers. I haven't written actual word problems here because it's hard to fit that in there in the space here. But you should make a list of your numbers like I have here so that it's organized and you can kind of clarify what's going on here. So we got actually what do we got? 7 numbers here, all with different units, but there's only one way to organize these in such a way that we end up with units of volume. We're looking for the liter to be our unit that we're trying to sort of glean out of all of this. So the only way to do this, we got 7 numbers, and we have to cancel the pressure units, the temperature units, and also the mole units. So again, think deeply about what you're seeing right here, and if you finally get it, you'll actually realize that this is relatively easy. I hate saying that if you're struggling with this, but you know, struggle long enough and eventually you will understand it. I have to believe. So the question now is, okay, now which numbers go where, what goes on top? So to simplify, you're going to think about each change individually. Forget about everything else except, for example, let's consider the pressure. The pressure is going down. So if the pressure goes down, then that plunger is going to go up and the volume will increase. So we want to put the larger number on the top of that fraction and the smaller number on the bottom. That, when multiplied times 6, will make the value go up. Okay, now forget about pressure. Just think about temperature. The temperature is going down. This will make the particles slow down, and the volume will want to decrease. Therefore, we're going to put the smaller number on the top and the bigger number on the bottom in that ratio. This will tend to make that 6 go down. Now forget about temperature. just think about the number of gas particles. If we blow some extra particles into that volume and increase the number of particles, the plunger will go up and the volume will increase. So we're going to put the large number on the top and the smaller number on the bottom. Simply do out your math, and we get an increase in volume of 10 liters. All right, I know that's a lot of stuff and a lot to think about, and I would suggest that you try both methods and practice thinking about what's going on here. It can't hurt to do that. You'll only increase your ability and capacity to think about complex problems and envision things by struggling with that a little bit. And eventually, I'm sure that you will have an aha moment